Sketch the graph for the function f of x equals x squared minus 1 to the 1/3 by determining the parts a through I. F of x equals x squared minus 1, a polynomial, the domain will be all real numbers, raised to a fractional exponent, the 1/3 power. The denominator of the fractional exponent is the root. It's an odd number here, and the domain of an odd root is all real numbers. So for part A, collectively the domain will be all real numbers, or negative infinity to positive infinity. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of a polynomial whose x term is to an even power, which will have y-axis or even symmetry, and a constant which always has y-axis or even symmetry. And then the entire thing is raised to a fractional exponent whose denominator, the root, is an odd number, and an odd root retains the symmetry. Since both terms inside of there will have y-axis or even symmetry, the 1/3 power will retain that even symmetry, and it is expected f of x will have even symmetry. F of negative x equals negative x squared minus 1 to the 1/3. A negative squared is a positive, and then x squared minus 1 to the 1/3 power. Comparing this result to the original, it exactly equals to it. So f of negative x equals f of x, which is the condition needed to have y-axis, also known as even symmetry. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate back into the original function, y equals f of 0, which will be 0 squared minus 1 to the 1/3 power. 0 squared is 0, minus 1 will be negative 1 to the 1/3 power. 1/3 power means cubed root in first power. The cubed root of negative 1 is negative 1 to the first power will be negative 1. We had an x-coordinate of 0. We found a corresponding y-coordinate of negative 1. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, can be set to be 0. And we want to solve for all x's. We can start by cubing both sides. Zero cubed is 0. X squared minus 1 to the 1/3 to the cube. We multiply the exponents, 1/3 times 3, which is 3 over 3, or 1. We'll leave just x squared minus 1, which can further factor, because it is a difference of squares, into x plus 1 and x minus 1. This has solutions of x equals negative 1 and x equals positive 1. We have a y-coordinate of 0. These are the corresponding x-coordinates, so we'll have negative 1, 0, and 1, 0 as the two x-intercepts. For part E, we want to determine the vertical asymptotes. F of x is a polynomial raised to a positive power. There is no denominator, so there will be none. part F, we want to determine any holes in the graph. F of x has no denominator, so there will be none. For part G, we want to determine the end behavior, horizontal asymptotes, and slant asymptotes. F of x is a polynomial to a fractional exponent that is positive. There is no denominator, so it will not have horizontal asymptotes or slant asymptotes. But because it is a polynomial raised to a fractional exponent power, we will have left-end and right-end behaviors of positive or negative infinity. We can determine the left-end behavior by taking the limit as x approaches negative infinity of the function x squared minus 1 to the 1/3 power. Plugging negative infinity in, negative infinity squared will be positive infinity, minus 1 will still be positive infinity, raised to the positive 1/3 power will be positive infinity. The right-end behavior can be determined by taking the limit as x approaches positive infinity of f of x, x squared minus 1 to the 1/3 power. Positive infinity squared is positive infinity, minus 1 is positive infinity, raised to the positive 1/3 power will be positive infinity. So it has left-end and right-end behaviors that are the same sign of infinity. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. The first derivative and the second derivative can be a little bit more involved here, so we can go to another page to work it out. So the original function is f of x equals x squared minus 1 to the 1/3 power. The first derivative will be a power rule. We'll bring the 1/3 power down, leave the inside alone, subtract 1 from the power, I will call that 3/3, and then multiply by the derivative of the inside to complete the chain rule. That'll be a 2x. We can put the constants together. There's a 2 that can move out with the 1/3. Multiplying the numerators 1 times 2 is 2 over the 3. We can move the x to the front. And then we have an x squared minus 1 to the 1 minus 3 negative 2/3 power. This is the version we will use to find the second derivative. But for the first derivative, we do want to have all powers be positive, so we will need to move that negative power to the denominator. The 2 stays in the numerator, the x stays in the numerator, there is a 3 in the denominator, and the x squared minus 1 will move to the denominator to become a positive 2/3 power. We want to fully factor the first derivative, so the numerator is fine as is, 2x. The denominator we can factor inside so that it is x plus 1 times x minus 1, it's a difference of squares, and the entire quantity to the 2/3 power. So the first derivative came out to 2x divided by 3 times x plus 1 times x minus 1 quantity to the 2/3 power. So we have the first derivative written as a single fraction, all powers are positive, it's fully factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, dividing both sides by 2 gives us x equals 0. From the denominator, since it is now factored, x equals -1 and x equals +1. We'll now check to see which of these are in the domain. The domain's all real numbers. 0, -1, and +1 are all real numbers. They're all in the domain. They're all critical numbers. We can now draw a domain line. It has no left end because it starts at -infinity. It has no right end because it ends at +infinity. We can put all critical numbers on here in order. -1 will come first, then 0, then +1. This splits the domain interval into 4 separate intervals. We can pick a test value in each of the intervals. The first interval, -infinity and -1, we can pick -10. The next interval, -1 to 0, there's no integer in there, but we can pick -1/2. 0 to +1, again, no integer in there, but we can pick +1/2. And the interval from 1 to +infinity, we can pick +10. We can test the trend by plugging these test values into the first derivative. We only care whether it's positive or negative, so we'll plug into the fully factored version, which is the version we have written right here. A couple of things about this. In the denominator, we have an entire quantity that's raised to the 2/3 power. 2/3 means cubed root and then square the result. Because the numerator, the power, is an even, squaring the result will make it always be positive. Times this 3 will still be positive, so the entire denominator will always be positive. And then in the numerator, that 2 is always positive as well. So the only term that determines whether it is positive or negative is the x. And that's the only place we need to plug in. So plugging in the test value of -10 will be -10. We have a negative first derivative, which corresponds to a decreasing trend. Plugging in a -1/2 will be a negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging in a +1/2 will be a positive. We have a positive first derivative. This corresponds to an increasing trend. And plugging in 10, we have a positive, again, corresponds to an increasing trend. Right at the critical number of x equals -1, we have the trend on the left decreasing and the trend on the right also decreasing. So the trend didn't change, but x equals -1 is a critical number. It actually came from the denominator. If it came from the numerator and the trend doesn't change, it'll be a plateau. If it comes from the denominator and the trend doesn't change, it's a cliff. So we have a cliff. It has an x-coordinate of -1 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of -1, which will be -1 squared minus 1 to the 1/3 power. -1 squared is 1, and then minus 1 to the 1/3 power. 1 minus 1 is 0, so we have 0 to the 1/3 power, which is 0, so we have a corresponding y-coordinate of 0. Right at the critical number of x equals 0, we have the trend change from decreasing to increasing, so x equals 0 will be a relative minimum. It has an x-coordinate of 0. It has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. Which is going to be 0 squared minus 1 to the 1/3. 0 squared is 0. So this is really just negative 1 to the 1/3 power, or the cube root of negative 1, which is negative 1. Right at the critical number of x equals positive 1, again we have the trend not changing. It's increasing on the left and increasing on the right. And x equals positive 1 also came from the denominator, so it will also be a cliff. It has an x-coordinate of positive 1. It will have a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 1, which is 1 squared minus 1, the entire thing to the 1/3 power. 1 squared is 1. Minus 1 to the 1/3 power. 1 minus 1 is 0 to the 1/3 power will be 0, so it has a corresponding y-coordinate of 0. For part I, we want to determine the intervals of concavity and any inflection points. All of this will require the second derivative. We can work that out on the other page. F double prime of x equals. It's best to take it from here, which will be a product rule of 2/3 x times x squared minus 1 raised to the negative 2/3 power. Product rule, derivative of the first will be a 2/3 times the second left alone, x squared minus 1 to the negative 2/3, plus the first left alone, 2/3 x, times the derivative of the second, which is a power rule. Bring the power down, negative 2/3. Leave the inside alone, x squared minus 1. Subtract 1 from the power, I will call that 3/3, and then multiply by the derivative of the inside to complete the chain rule. The first term we'll leave as is. For the second term, we can put all the constants together. We have a 2/3, a negative 2/3, and a 2. Multiplying the numerators, 2 times negative 2 is negative 4 times the 2 is negative 8. And then multiplying the denominators, 3 times 3 is 9, so negative 8 over 9. There is an x and an x squared. And there is an x squared minus 1 to the negative 2/3 minus 3/3, negative 2 minus 3, negative 5 thirds power. We will want to fully factor the second derivative. There is a common factor in the numerator of a 2 because of the 2 and the 8. So we can factor out a 2. In the denominator, there's a 3 and a 9. What we can do is give them a common denominator, so instead of writing this as 2 over 3, we can think of it as 6 over 9. And we can then factor out the 9. Now, if we take out the 2, this will become a 3. And if we take out the 9, it will just be a 3. So we'll take out a 2 over 9. And we can also factor out an x squared minus 1. To the lower of the two powers, we have a negative 2/3 power and a negative 5/3. Negative 5/3 will be lower by being more negative. Negative 5/3 power. What's left will be, again, we're going to think of the 2/3 multiplying by 3 over 3 as a 6 over 9. Factoring out the 2 in the numerator, this will become a 3, and this will become a 4. Factoring out the 9 in the denominator, these will disappear. And then factoring out the x squared minus 1 to the negative 5/3 power. Factoring is division. Division is subtraction of exponents. We would be subtracting a negative 5/3, which is equivalent to adding a 5/3 to each of the powers. This power plus 5/3, negative 2 plus 5 is 3/3, or 1. This entire thing will become a power of 1. And we have left a 3 times an x squared minus 1. Adding a 5/3 to this power will become a 0, and anything raised to 0 is a 1. And we'll have a minus 4 and x squared. So we'll have 3 times x squared minus 1, and then minus 4x squared. Three times x squared minus 1, and then minus 4x squared. So this is 2/9 x squared minus 1 to the negative 5/3 power. We can distribute the 3 in here, which will be 3x squared minus 3. And then we have the negative 4x squared. We can combine like terms together inside of the square brackets. We'll leave the x squared minus 1 to the negative 5/3 alone. I will turn the square brackets into parentheses now. 3x squared minus 4x squared will be a negative x squared, and there is a minus 3. We can factor a negative out of here. It will move all the way to the front. So we have a negative 2/9 x squared minus 1 to the negative 5/3. And factoring the negative out, we'll leave a positive x squared and a positive 3. We want all powers to be positive in the second derivative. So we're going to move the negative 5/3 power to the denominator. The negative and the 2 can stay in the numerator. There's also an x squared plus 3. And in the denominator, there will be a 9. And an x squared minus 1 to the positive 5/3 power. We want to fully factor the second derivative. The numerator is a sum of a square term, so it cannot factor any further, and will have to be left as x squared plus 3. In the denominator, it is possible to factor the difference of squares. It will be x plus 1, and x minus 1, and the entire thing will be to the 5/3 power. We can now put this in for our version of the second derivative. So we had a -2, x squared plus 3, a 9, and then an x plus 1, an x minus 1, and the entire thing to the 5/3 power. So we have the second derivative as a single fraction. All powers are positive. It is fully factored. We can set the numerator equal to 0. We can set the denominator equal to 0 and solve for all x's. From the numerator, the -2 can divide over. We can subtract 3, so x squared will equal -3, and x will equal plus or minus the square root of -3. For the denominator, it's fully factored, so we can see that x will equal a -1 and x will equal a +1. We'll check to see which of these are in the domain. The domain's all real numbers. X equals positive or negative the square root of -3 will not be a real number because it's an even root of a negative number, so these will not be in the domain, and we can cross them out. X equals -1, x equals +1 are in the domain, and they are candidate numbers. We can now draw a domain line. It has no left end because it begins at -infinity, no right end because it ends at +infinity. We can put each of the candidate numbers on here in order. -1 will come before +1. This splits the domain interval into 3 separate intervals. We can pick a test value in each of the intervals. The first interval, -infinity to -1, we can pick -10. The second interval, -1 to +1, we can pick 0. Third interval, 1 to +infinity, we can pick +10. We can test the concavity by plugging these test values into the second derivative. We only care whether it is positive or negative. So we'll use the fully factored version, which is this version here. A couple things about this. In the numerator, there is an x squared, which will always be positive, plus 3, which will always be positive. So that entire thing is positive. Times the -2. So the numerator is always going to be negative here. And in the denominator, the 9 is always positive. So we will just need to worry about this. It's to the 5/3 power here, so those are both odd, numerator and denominator of the 5/3 power. So that can be positive or negative. And then because of the -2 in the numerator of the second derivative, it'll end up being opposite sign of that. So the only place that needs to be plugged in is here. And then be sure to account for the negative already existing in the numerator. Plug in the test value of -10 in the denominator. -10 plus 1 is a negative. Negative 10 minus 1 is a negative. Negative times negative is a positive. Positive to the 5/3 power will be positive. And we have the negative 2 over the positive. Negative over positive is negative. We have a negative second derivative. This corresponds to concave down. Plugging in 0, 0 plus 1 is positive. 0 minus 1 is negative. Positive times negative is negative. Negative to the 5/3 power, because they're both odd, will be negative. The numerator is a negative over the negative, which will be positive. We have a positive second derivative. This corresponds to concave up. Plugging in the test value of 10 into the portion of the second derivative that matters. 10 plus 1 is positive. 10 minus 1 is positive. Positive times positive is positive. To the 5/3 will still be positive. We have the negative 2 over that. Negative over positive is negative. We have a negative second derivative. This corresponds to concave down. Right at the candidate number of x equals -1, we have the concavity changing from concave down to concave up. So x equals -1 will be an inflection point. It has an x-coordinate of -1 and a corresponding y-coordinate that can be found by plugging the x-coordinate into the original function. So y equals f of -1, which we have evaluated already, but we can write it here again. It'll be -1 squared, which is +1, minus 1 to the 1/3 power. 1 minus 1 is 0. To the 1/3 will be 0, so that's a corresponding y-coordinate of 0. And right at the candidate number of x equals +1, again, we have the concavity changing, this time from concave up to concave down, so x equals +1 will also be an inflection point. It has an x-coordinate of +1, and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 1, which will be 1 squared minus 1 to the 1/3 power, which is also 1 minus 1 to the 1/3 power. 1 minus 1 is 0 to the 1/3 power will be 0, has a y-coordinate of 0. We can now draw the graph. We have a vertical axis and a horizontal axis. The domain is all real numbers. We found that it will have y-axis or even symmetry. That means that the graph will be a mirror image of itself over the y-axis. So whatever we see over here, we will see its mirror image or its flip over the y-axis over here. We will be sure that that is the case. We have a y-intercept of 0, -1. That will be down here somewhere. We can label that. We have two x-intercepts, one at -1, 0 and one at +1, 0. This would be the -1, 0 over here. +1, 0 over here. We have left-end behavior of positive infinity and right-end behavior of positive infinity. Left-end behavior of positive infinity means it'll end up here on the left end, and right-end behavior of positive infinity means it'll end up here on the right. So we'll be sure that that is the case. Right at -1, 0, we have a cliff. A cliff is where the tangent line goes vertical. Cliffs are always inflection points. We can see it as an inflection point over here. It is concave down on the left and concave up on the right. So it'll look something like this. It'll be concave down this way and concave up this way. And it goes vertical for the tangent line right there. Right at the point of 0, -1, we have a relative min. So we can give that a relative min type of shape. Something like so and like so. And right at the point 1, 0, we have another cliff. Now it is also an inflection point because all cliffs are, and it will be concave up on the left and concave down on the right. Being a cliff, the tangent line will go vertical there. So I have a shape something like so. Now from here, we can connect these pieces together. So here it'll go like so. And like so. It'll continue to curve off somewhere this way. And then over here we can connect these pieces together. Like so. And then over here it will also curve off because it's supposed to be concave down on the interval from -infinity to -1 as well as +1 to +infinity, so it should be curving downward on both of those two, and it is. So it has a domain of all real numbers. It does cover all x values. It should be showing the even symmetry, and we can see that this piece flipped over the y-axis, or mirror image over the y-axis, will give that piece. So it is showing the symmetry, as it should. And it does have the left end behavior of +infinity and the right end behavior also of +infinity, as it should. All properties are being met. This is therefore the graph of f of x.